Today, we are opening up the hood on what might be the most sophisticated high-pressure filtration system known to engineering.
It really is.
And I don't mean in a factory or, a water treatment plant. I'm talking about the kidney.
It is arguably the most underrated organ in the mammalian body. We tend to think of it as just a waste disposal unit, but as we'll see today, it's really a master chemist and a hydraulic engineer all wrapped into one.
And to set the stakes, I want to start with a number. A number from the research stack that, it actually made me pause and reread the page.
I think I know which one you mean.
The number is 180 liters.
It's a massive number.
That is the amount of fluid the human kidneys filter every single day. 180. I was trying to visualize this. A standard large industrial oil drum is what, about 159 liters?
Right around there, yes.
So every day, your kidneys are processing more than a full industrial drum of fluid derived directly from your blood.
That's a great way to picture it. And if you want to look at it relative to the body itself, the average human has about, say, 3 liters of plasma, the liquid part of the blood.
Okay, 3 liters.
So the kidneys are filtering your entire plasma volume roughly 60 times a day.
60 times?
Every 24 minutes, your entire blood supply gets a complete scrub down.
But here's the mystery, and this is the paradox that really drives this entire deep dive.
Yeah.
We filter 180 liters, but we only pee out, what, about 1 liter a day? Maybe 1.5 liters.
Roughly 1 to 1.5 liters, yes. That's a normal range.
So do the math. The body pushes 180 liters out of the blood, and then it frantically scrambles to pull 179 liters of it back in.
Mm-hmm.
That seems incredibly inefficient. It's like cleaning your house by throwing all your furniture out on the front lawn and then, dragging 99% of it back inside.
That is the reabsorption mechanism. Mm-hmm. And while it sounds inefficient, it's actually a strategy for extreme precision. But you're right about the risk. If that dragging back in process fails,
Yeah.
if reabsorption drops by even a small percentage, say 10%, you wouldn't just be dehydrated. You would deplete your entire circulatory volume in a matter of minutes.
That's the high-stakes game we're talking about. If the kidney blinks, you go into shock.
Exactly. So our mission today is to understand how this machinery works without killing us. We need to look at the sieve, the glomerular capillary membrane, which is this atomic-level filter.
Okay.
Then we need to break down the physics, the specific pressures that drive this filtration. And finally, we need to understand the control dials, the auto-regulation that keeps this flow steady whether you're asleep or sprinting.
All right, let's do it. Part 1, the machine. We are zooming in on the glomerular capillary membrane. Now, I know what a capillary is. It's a tiny blood vessel. But the source material makes it very clear that this is not your average capillary.
No, it's completely unique. A standard capillary, say in your bicep, is designed to be just permeable enough to let some oxygen and a little glucose out. But the glomerular capillary is a fire hose.
A fire hose?
It has a filtration capacity that is hundreds of times higher than a skeletal muscle capillary.
Hundreds of times. So structurally, it has to be built differently. There's no other way.
It is. It's a 3-layer sandwich, and every single layer is designed to solve a specific problem in the filtration process.
Okay, so let's peel the onion. Layer 1.
Layer 1 is the endothelium. This is the inner lining of the blood vessel itself. In a normal vessel, this is a smooth, continuous wall of cells. But in the kidney, it is perforated by thousands of holes called fenestrae.
Fenestrae, which literally means windows, right?
Yeah, exactly. Imagine a pipe where the walls are just riddled with open windows. This allows the plasma, the water, the salts, the sugars to flow through with almost zero resistance.
So it's wide open.
It is, but there's a catch. The cells of this endothelium are coated with fixed negative electrical charges.
Okay, hold that thought. Negative charges. Why does that matter right at the entrance? Why is that the first feature we're talking about?
Well, think about what is floating in your plasma. You have water and salt, which are neutral or they're very small ions. But you also have plasma proteins. And the most important one is albumin.
And albumin carries a negative charge.
Correct. So right at the first gate, you have negative charges on the wall repelling the negative charges on the proteins. It's an electrical balancer.
I like that. So water flows through the window, proteins get pushed back. That's layer 1. What about layer 2?
Layer 2 is the basement membrane. Think of this as the foundation. It wraps around the endothelium. It's a complex meshwork of collagen and proteoglycans.
The text describes it almost like a felt or a dense fiber mat.
That's a good analogy. It has large spaces, so water and small solutes like glucose or sodium can drift through this mesh pretty easily. But, just like the endothelium, the proteoglycans in this mesh are very, very strongly negatively charged.
I'm sensing a theme here. The kidney is building an electrostatic force field.
It absolutely is. This basement membrane is the real heavy lifter of the operation. It prevents the bulk of plasma proteins from ever getting close to leaking through.
Okay, so we've got the windowed endothelium, then the charged mesh of the basement membrane. What's the final layer? Layer 3. The podocytes. This sounds like an alien species.
The epithelial cells, or podocytes. Podo means foot. These cells are on the outside of the capillary. They have these long, finger-like extensions called foot processes, or pedicels.
So they are hugging the capillary.
They are wrapping around it, interlocking with each other like the fingers of two hands clasped together.
Oh, okay.
And in the spaces between those fingers, you have tiny gaps. These are called slit pores.
And let me guess, the slit pores are negatively charged.
You guessed it. So, for a molecule to leave the blood and start its journey to becoming urine, it has to pass through the fenestrae window, navigate the basement membrane mesh, and squeeze through the podocyte slit pores, all while running this gauntlet of negative electrical charges.
So we have a mechanical filter, the holes and the slits, and we have an electrical filter. I want to dig into the data on this because the source material had a table 27 to the 1, that breaks down what calls filterability.
This table is the key to understanding the selectivity of the whole system. They set water as the baseline, filterability of 1.0.
Right, and I saw that glucose and inulin also have a filterability of 1.0.
Meaning they pass through as freely as water does. The filter effectively ignores them. But then look at albumin.
Albumin has a molecular weight of 69,000. It's a big molecule. Its filterability is 0.005.
Basically zero. The concentration in the filtrate is less than 1% of what it is in the plasma. But here's the crucial question, and this is where the science gets really cool. Is albumin blocked because it's too big or because it's negatively charged?
And this is where the dextrin experiment comes in. I want you to walk me through this because this proves the mechanism beyond a doubt.
Right. So researchers use dextrans, which are basically polysaccharides long sugar chains. The beauty of dextrans is that you can synthesize them to be any size and any charge you want.
So they made a dextrin that was the exact same size as an albumin molecule.
Yes, an effective radius of about 36 angstroms. First, they used a neutral dextrin, no charge at all.
And what happened?
The filterability was about 0.15 or 0.20.
Okay, so wait. Water is 1.0. Albumin is 0.005. A neutral blob of the same size is 0.20. That means the size alone blocks some of it, but a significant amount still gets through.
Exactly. If the kidney relied only on whole size, we would be leaking a lot of protein all the time. But then they took that same 36 angstrom dextrin and made it polycationic positively charged.
And since the filter is negative, opposites attract.
The filterability shot up to 0.4. The kidney practically sucked the molecule in.
Wow.
And finally, the clincher. They made a polyanionic dextrin, negatively charged, same size, 36 angstroms.
Just like albumin.
And the filterability dropped to 0.01.
There it is. From 0.20 for neutral down to 0.01 just by adding a negative charge.
Precisely. So albumin isn't just too big, it's magnetically rejected. The pores are about 8 nanometers wide, and albumin is about 6 nanometers. It should fit, but the electrostatic repulsion keeps it out.
That distinction explains the pathology mentioned in the text, minimal change nephropathy.
Yes. This is a condition, quite common in children, where a patient suddenly starts peeing out massive amounts of protein. It's called proteinuria.
But when they look at the kidney under a light microscope...
But it looks totally normal. The holes aren't bigger, the cells aren't dead. That's why it's called minimal change. But if you look at the physics, what's happened is the negative charges on the podocytes have been neutralized, likely by some kind of immune response.
So the electrical fence is down?
The fence is down, the physical wall is still there, but without that charge, the albumin just slips right through the fenestrae and the slits. It proves that the charge is just as important, if not more important, than the physical architecture.
That is a brilliant piece of detective work. So we have a charged sieve, but a sieve is useless unless you push something through it. This brings us to part 2, the physics.
The hemodynamics, yes. The forces at play.
We have a formula for GFR, the glomerular filtration rate. It says GFR equals Kf times net filtration pressure. I want to break this down variable by variable. Let's start with Kf.
Okay, Kf is the filtration coefficient. In plain English, it's a measure of how leaky is the membrane, multiplied by How much surface area do you have?
And we already established that the kidney is incredibly leaky.
Yes. The KF for the kidney is about 4.2 milliliters per minute per millimeter of mercury. To give you some context, that is about 400 times higher than the KF of a capillary in, say, your muscle.
400 times. But this number isn't set in stone. The text mentions that diseases can change KF.
Right. Think about chronic hypertension, high blood pressure, or uncontrolled diabetes. Over years and decades, these conditions cause the basement membrane to sicken. It becomes dense and fibrous.
Because the filter gets clogged up.
Effectively, yes. The leakiness drops. Or you can lose capillaries entirely. You lose surface area. In both cases, KF goes down. And if KF goes down, GFR goes down. You filter less blood.
Okay, so that's the coefficient. Now let's talk about the push, the net filtration pressure. The text describes this as a tug of war between really four forces.
Exactly. You have forces pushing fluid out of the blood and forces trying to keep it in or push it back down.
Force number one, the glomerular hydrostatic pressure, PG.
Okay.
This is the main engine.
This is the blood pressure inside the glomerular capillary.
Yeah.
And it is remarkably high. In the kidney, it's maintained at about 60 millimeters of mercury.
Why is 60 so significant?
In most other capillaries in your body, the pressure is somewhere between 15 to 30 millimeters of mercury. The kidney deliberately maintains a pressure twice as high as the rest of the body's capillary beds. It needs that brute force to drive filtration.
Okay, so we have 60 millimeters of mercury pushing out. Now, who is pushing back?
First, you have the pressure in the container that's catching the urine. That's Bowman's capsule. This is Bowman's capsule hydrostatic pressure, PB. Fluid is filling up this space, so it pushes back against the capillary wall. That's usually about 18 millimeters of mercury.
So 60 pushing out, 18 pushing back. The net force is 42.
But we're missing the invisible hand, the proteins.
The colloid osmotic pressure.
Right. Remember, the albumin didn't get out. It's still stuck in the blood. And proteins love water. They exert a kind of magnetic pull on the water, trying to hold it inside the capillary. This is the glomerular capillary colloid osmotic pressure, PG.
And the value for that?
On average, it's about 32 millimeters of mercury.
Okay, so let's do the final math. 60 pushing out minus 18 pushing back minus 32 sucking back in.
60 minus 50. The result is a positive 10 millimeters of mercury.
That's it. 10.
10.
We are filtering 180 liters a day, scrubbing the entire bloodstream 60 times over on a net pressure margin of just 10 millimeters of mercury.
It is razor thin. And that should scare you, because it means a small shift in any one of those numbers can crash the entire system.
Let's play out a scenario from the text. Kidney stones.
A classic example. Let's say a stone gets lodged in the ureter. The urine can't drain to the bladder.
So the plumbing backs up.
It backs up all the way into the kidney, into Bowman's capsule. So the hydrostatic pressure in the capsule, PB, starts to rise. It's normally 18. Let's say it goes up to 28.
So now we have 60
And
minus 28 minus 32.
0.
Filtration stops.
Exactly. The kidney shuts down not because of a problem with the blood flow, but because the back pressure equals the forward pressure. This leads to a condition called hydronephrosis, a distended, water-filled kidney that can be permanently damaged if it's not fixed.
Wow. Now, there is a nuance in the physics section that I really struggled with, and I want you to explain it. We used 32 as the average osmotic pressure, but the text says this pressure actually changes as the blood moves through the capillary.
This is a critical concept called filtration equilibrium. Imagine the blood entering the capillary at the afferent end. It hasn't been filtered yet. The protein concentration is normal. The osmotic pressure at that point is about 28 millimeters of mercury.
Okay, so at the very start, you have 60 push, minus 18 back, minus 28 suck. That's a net pressure of positive 14. Strong filtration.
Right. But as the blood travels along the length of the capillary, we are squeezing water out through the fenestrae. But the protein stays behind.
So the blood gets thicker, like you're boiling down a sauce.
That is the perfect analogy. The protein concentration rises by about 20%. By the time the blood reaches the exit, the efferent arteriole, the osmotic pressure has risen from 28 all the way to 36 millimeters of mercury.
So the suck-back force gets stronger the further you go down the line.
Yes. And this acts as a natural brake on the system. If the osmotic pressure rises too high, say to 42, it would completely cancel out the hydrostatic push. Filtration would stop before the blood even leaves the capillary.
This implies that the rate of blood flow is incredibly important.
Hugely. If you have a very high filtration fraction, meaning you try to filter too much of the plasma at once, the proteins get so concentrated so quickly that they choke off the process. The physics limits itself.
That leads us perfectly to part 3, the control dials. Because if the system is this sensitive, operating on a +10 margin, we need a way to stabilize it.
We do. We need to control that 60 millimeter of mercury hydrostatic pressure, the PG. And the body does this primarily with 2 valves, the efferent arterial, which is the input, and the efferent arterial, the output.
Okay, this seems simple at first glance. If I constrict the efferent arterial, the input I block flow into the glomerulus, pressure drops, GFR drops.
Correct. Kink the hose before the nozzle, the spray dies down.
But the efferent arterial, the output valve, this is where the text describes a biphasic effect. And I want to slow down here because this is really counterintuitive.
It is the most common stumbling block for students of physiology. Let's walk through it. Imagine you have that hose, and you put your thumb over the end of it. You constrict the outlet.
The pressure inside the hose builds up. It sprays harder.
Right. So initially, mild constriction of the efferent arterial causes blood to back up in the glomerulus. The glomerular pressure, PG, rises, and GFR goes up.
Okay, that follows a logic. Constrict the output, you increase the pressure, you increase the filtration.
What happens to the rate of flow of blood through the hose?
It slows down. I mean, you're blocking the exit.
Exactly. The renal blood flow drops. Now, remember our boiling the sauce analogy. If the blood is moving very slowly through the capillary, it's sitting there for a long, long time.
So you have more time to filter water out.
You filter a massive amount of water relative to the flow. The filtration fraction spikes.
And if you filter too much water, the protein concentration shoots up.
And the colloid osmotic pressure skyrockets.
Ah, I see the trap. You increase the hydrostatic pressure, the push, by squeezing the exit, but you inadvertently increase the osmotic pressure, the pull, even more because you stalled the flow.
Exactly. The osmotic suck back overpowers the hydrostatic push. So if you constrict the efferent arterial too much, GFR actually plummets.
That is the biphasic effect. A little bit of constriction helps, a lot of constriction kills it.
It's a bell curve.
Yeah.
And the body rides this curve very carefully, especially when it's using hormones like angiotensin II, which we'll get to in a bit.
Before we get to the hormones, let's briefly talk about the fuel. Part 4, renal blood flow. We said it's 1,100 milliliters per minute.
Which is about 22% of your total cardiac output. The kidneys are tiny, 0.4% of your body weight. Yet they demand a quarter of your blood with every heartbeat.
Is that just to keep the tissue alive? I mean, is it a very hungry organ?
That's the logical assumption, but no. If you compare the oxygen levels in the renal artery versus the renal vein, the difference is actually quite small. The kidney isn't using that blood for its own metabolism in the traditional sense. It needs that sheer volume to supply the hydraulic pressure for filtration.
It's a plumbing issue, not a metabolic one.
Primarily, yes. But there's a metabolic cost. The source material shows a direct, almost linear link between oxygen consumption and sodium reabsorption.
Right.
This is a key insight. We filter 180 liters. That fluid is salty. It's full of sodium. To save your life, the kidney has to actively pump all that sodium back into the blood against the concentration gradient.
And pumps run on ATP, which requires oxygen.
Correct. So the kidney's oxygen bill is directly proportional to how much sodium it has to reabsorb.
So what happens if GFR stops, say in that kidney stone scenario we talked about?
If GFR stops, you aren't filtering sodium, so you don't need to pump it back. The kidney's oxygen consumption drops to almost nothing, just the basal level needed to keep the cells from dying, about a quarter of its normal use.
That's fascinating. It's an engine that only burns fuel when it has actual work to do.
Precisely. It's incredibly efficient in that regard.
Let's move to part 5. Neurohormonal control. We have the valves. Who is turning them?
We have the nervous system and the endocrine system. Let's start with the nerves. The sympathetic nervous system.
The fight or flight response.
Yes. The text calls this the emergency system. Under normal, moderate stress like giving this presentation, your renal sympathetic nerves are pretty quiet. They don't have much of an effect.
But if I get into a car accident?
If you have a severe hemorrhage or brain ischemia or some other major crisis, the alarm bells ring. The sympathetic system clamps down on everything. It constricts both the efferent and efferent arterioles violently.
To stop the kidney from working.
To shunt blood to the heart and brain. If you are bleeding out, making urine is not a priority. The kidney sacrifices its own blood flow to help keep your systemic blood pressure up.
That makes perfect sense. Now, hormones. The text lists epinephrine and norepinephrine, same idea, right? Adrenal stress hormones?
Yes, from the adrenal medulla. They have the same effect. They constrict. Then there is endothelin.
That sounds like a sinister chemical.
It's a marker of damage. It's released by damaged blood vessels. It's one of the most powerful vasoconstrictors the body can produce. We see high levels of endothelin in conditions like toxemia of pregnancy or preeclampsia and in acute renal failure. It contributes to the kidney shutting down.
But the real star of the show here seems to be angiotensin II. The text calls it the protector.
It is the most interesting one, for sure. Let's paint a scenario. You are stranded in a desert. You haven't had water in 24 hours. Your blood volume is dropping. Your blood pressure is starting to sag. Your body senses this and releases renin, which eventually leads to the creation of angiotensin II. Now, based on what we discussed about that biphasic effect, angiotensin II has a superpower. It preferentially constricts the efferent arteriole, the outlet.
It puts the thumb on the end of the hose.
Right. Why is that a brilliant move in this specific situation?
Well, my systemic blood pressure is low because I'm dehydrated, so the flow into the kidney is weak. By constricting the exit, angiotensin II builds up pressure inside the glomerulus.
Exactly. It artificially props up the Petri sheet to keep GFR as normal as possible, even though your systemic pressure is crashing. It keeps the filter running so you can still clear metabolic wastes.
But it does something else too, right? Something downstream.
Yes. By constricting the efferent arteriole, it reduces the blood flow into the capillaries that come after the glomerulus, the peritubular capillaries that wrap around the tubules.
So the pressure in those downstream capillaries drops.
And low pressure downstream facilitates reabsorption.
Yeah.
It makes it much easier for those capillaries to suck up salt and water from the tubules to reclaim every last drop.
That is genius. So angiotensin II keeps the filter working. A&D helps suck back every drop of water to save me from dehydration.
It is the ultimate survival hormone for the kidney.
But every system needs a break. The text talks about the dampeners, nitric oxide, and prostaglandins.
Right. You don't always want constriction. Nitric oxide, or NO, is constantly released by the endothelium just to keep vessels relaxed and maintain a baseline flow. But I want to focus on prostaglandins, specifically PGE2 and PGI2.
These are vasodilators. They open the valves.
They oppose vasoconstriction. They are the buffer. If angiotensin II is clamping down hard, prostaglandins are pushing back a little to prevent the kidney from closing down completely.
And this brings us to the very real-world clinical application regarding NSAIDs, ibuprofen, aspirin, naproxen.
This is a vital warning for you and for anyone listening. NSAIDs work by blocking an enzyme called cyclooxygenase, or COX. This stops the production of prostaglandins. That's how they reduce pain and inflammation.
But if they stop prostaglandins in the kidney...
Let's go back to our desert island, or even just a dehydrated senior with the flu scenario. You have high levels of angiotensin II clamping down on the vessels to maintain pressure. The only thing keeping the afferent arteriole from slamming shut is the local production of prostaglandins.
It's the only thing holding the door open.
Exactly. If you take a high dose of ibuprofen, you kick that doorstop away. The prostaglandins vanish. The unopposed vasoconstriction slams the afferent arteriole shut.
And GFR crashes, acute renal failure.
Precisely. If you're young, healthy, and well-hydrated, NSAIDs are generally fine. But if you're volume depleted for any reason, they can be very dangerous to the kidneys.
That is a massive takeaway. Now, moving to part 6, autoregulation. We've talked about hormones, which are external signals. But the kidney has its own internal brain.
It does. It's called autoregulation. The kidney has this remarkable ability to maintain a constant GFR and blood flow, even if your systemic arterial pressure swings from, say, 75 millimeters of mercury all the way up to 160.
That is a huge range.
It is, and it has to be. Because if GFR rose linearly with blood pressure, say your pressure went up 25% and GFR went up 25%, you would filter an extra 45 liters a day.
And if reabsorption didn't keep up perfectly,
you would lose your entire blood volume into your urine in a couple of hours. This entire mechanism is about preventing pressure diuresis, peeing yourself to death, just because your blood pressure went up a little bit.
So how does it work? The text details 2 main mechanisms. The first is the tubuloglomerular feedback, TGF.
This relies on a beautiful piece of anatomy called the juxtaglomerular complex.
I love that term. Juxta means next to.
Yes. The distal tubule, the tube carrying the processed urine, actually loops back and physically touches the afferent and efferent arterioles of its own glomerulus.
It's checking its own work.
Exactly. And in the wall of that tubule, right where it makes contact, there are specialized cells called the macula densa.
The dense spot, what do?
They are chemoreceptors. They taste the fluid passing by. Specifically, they sense the concentration of sodium chloride, salt.
Why is salt the signal?
Salt is a proxy for flow speed. This is the tricky part, so listen closely. The loop of Henle, the section of the tubule just before the macula densa, is responsible for reabsorbing salt. But this process takes time.
Okay.
If GFR is high, the fluid is rushing through the loop. It's moving very fast.
So the loop doesn't have enough time to grab all of the salt.
Correct. So a lot of salt arrives at the macula densa. High salt means high flow.
Okay, that makes sense. High GFR leads to fast flow, which leads to high salt at the sensor. What does the macula densa do when it tastes all that salt?
It panics. It sends out a signal, likely adenosine, which acts locally to constrict the afferent arteriole.
It shuts the inlet valve,
Which lowers the pressure in the glomerulus, which lowers GFR and slows the flow back down to normal.
Okay, now play it in reverse. What if GFR is too low?
If GFR is low, the fluid moves sluggishly through the loop. The loop has all the time in the world to suck every last grain of salt out.
So the fluid reaching the macula densa is practically salt-free.
Low salt means low flow. The macula densa senses this and sends two distinct signals. First, it tells the afferent arteriole to dilate, open up.
Let more pressure in.
And second, it signals the nearby juxtaglomerular cells to release renin, which, as we know, creates angiotensin II.
Which constricts the efferent arteriole.
So you open the inlet and you constrict the outlet. The pressure in the glomerulus rises. GFR is restored.
It's a self-correcting thermostat. That is incredibly elegant.
It is, I think, one of the finest feedback loops in all of biology.
And briefly, the second mechanism, the myogenic one.
That's much simpler. It's an intrinsic reflex of vascular smooth muscle. If you blast a blood vessel with high pressure, the wall stretches.
Like blowing up a balloon.
But unlike a balloon, the muscle cells react to that stretch by opening calcium channels. Calcium rushes in, and the muscle contracts.
So you push, and it pushes back.
Instantly. This prevents the delicate glomerular capillaries from being blown out by a sudden spike in your blood pressure.
Okay, part 7. Diet and environment. We've built this perfect machine. How do we mess it up? The text mentions a high-protein meal.
The meat sweats effect. It's very interesting. A high-protein meal can increase GFR and renal blood flow by 20 to 30%.
Why? Is it just the extra work of getting rid of waste?
It's actually a clever hack of the macula densa system we just discussed. When you eat a lot of protein, your blood is flooded with amino acids.
Okay.
The kidney filters these amino acids, but it wants to keep them. They're valuable. So in the proximal tubule, it reabsorbs them aggressively.
Makes sense.
But here's the mechanism. The transporters that pull amino acids back into the blood are co-transporters. They have to pull a sodium ion along with the amino acid.
Ah. So to save the protein, we have to pull a lot of extra salt out of the tube early on.
A lot of salt. So by the time the fluid gets down to the macula densa,
The salt is
the
gone.
macula densa tastes low salt.
And it thinks, oh no, the GFR is too low, the flow is slow.
Exactly. Even though the flow is actually normal or even high, the sensor is tricked. It triggers the feedback loop, dilate the afferent arteriole.
So GFR goes up.
It causes a state of hyperfiltration. Evolutionarily, this is probably a good thing. It helps you clear the urea waste from the protein more quickly, but it does force the kidney to work overtime.
And the text connects this directly to diabetes.
Yes, this is a critical connection. In uncontrolled diabetes, you have high blood glucose. Glucose is also reabsorbed in the proximal tubule via a sodium co-transporter, SGLT2,
So high sugar in the tube means high sodium reabsorption.
which means low salt at the macula densa, which triggers the exact same feedback loop to dilate the afferent arteriole.
So the diabetic kidney is constantly in a state of hyperfiltration.
Constantly running at 120% capacity, day in and day out. This chronic high pressure and high flow eventually causes the glomerulus to scar and harden. This is called glomerulosclerosis. This is why diabetes is the leading cause of kidney failure. We literally burn out the filter.
That is a profound connection. It's not the sugar being toxic directly. It's the hemodynamic response to the sugar that causes the damage over time.
Exactly. It's a failure of regulation.
And finally, aging. The text was blunt here.
It is unavoidable. After age 40, GFR tends to drop by about 10% per decade. You simply lose functional nephrons as you get older. By age 80, your kidney function might be half of what it was at age 20.
Which just emphasizes why we need to protect what we have.
Indeed.
We have covered a massive amount of ground. Let's try to recap the journey for the listener.
We started with the shear scale, 180 liters filtered per day. Then we dissected the filter, the fenestrated endothelium, the negatively charged basement membrane, and the podocytes, all designed to repel proteins like albumin. Then we balance the physics. The tiny positive 10 millimeter of mercury net filtration pressure, which is a constant tug of war between the 60 millimeter hydrostatic push and the rising colloid osmotic pull.
Then we looked at the control dials, the afferent and efferent arterioles. We explored that biphasic trap, where too much efferent constriction actually kills GFR by spiking the osmotic pressure.
And we marveled at the autoregulation, the macula densa tasting the salt in the urine to keep the flow perfectly constant.
And we applied it to real life, why dehydration and NSAIDs are a dangerous mix, and how high protein or high sugar diets can trick the kidney into working itself to death.
That's the whole story in a nutshell.
I want to leave the listener with one final provocative thought. We spent a lot of time talking about the energy cost. The kidney consumes twice as much oxygen as the brain, gram for gram. And it does this to filter 180 liters just to reabsorb 179. From an engineering standpoint, this just seems like a terrible design. Why throw everything out just to take most of it back? Why not just have a filter that specifically picks out the toxins and leaves the good stuff, the water and salt, in the blood?
It's the ultimate quality control philosophy.
Yeah.
Imagine you have a messy drawer in your kitchen. Option A. You rummage through it and try to pick out the specific pieces of trash you see. But if there's a piece of trash you don't recognize, you probably leave it.
You dump the entire drawer out on the floor. Then you pick up only the things you know are valuable, your forks, your knives, your spoons, and you put them back. Everything else on the floor gets swept away.
That's the kidney.
That is the kidney. It operates on a whitelist system, not a blacklist. By dumping everything out through filtration and then only having specific transporters to save the good stuff through reabsorption, it guarantees that any new toxin, any strange drug, or any metabolic waste product that the body doesn't have a name for gets flushed.
That's expensive, but it guarantees purity.
Exactly. It's a system designed for a world full of unknown threats.
That is a beautiful way to close. Thank you for this deep dive.
My pleasure.
And to our listener, go drink a glass of water. Your Megalidens is watching. See you next time.